Science has theories so shocking that even experts hesitate to discuss them. These ideas don't just challenge what we know, they make us question reality itself. What if everything we trust, logic, predictability, even time, is an illusion? What if tiny, unnoticed changes could trigger massive events? Today we're diving into one of the most unsettling theories in science. The idea that chaos isn't just part of nature, but the very foundation of existence. Get ready, because once you learn this, you may never see the world the same way again. You've probably heard that a butterfly flapping its wings in Brazil could cause a tornado in Texas. It sounds extreme, but there's real science behind it. Our world follows both randomness and strict rules. Randomness means small events can trigger massive, unpredictable outcomes. Strict rules suggest everything follows cause and effect, meaning the future could be predicted if we knew all the details. But how do these two forces interact? Can tiny actions really shape the world? This is the heart of chaos theory, a field uncovering hidden patterns in what seems completely unpredictable. Scientists are only beginning to understand how chaos and order connect in our universe. Chaos theory studies systems that follow clear rules, meaning their future should, in theory, be predictable. However, because even the smallest changes in their starting conditions can lead to drastically different outcomes, accurately predicting their long-term behavior is impossible. This theory is important because it reveals how everything is interconnected. Any structured entity, whether a living being, a war, a story, or a flock of birds, is a system. If it evolves over time, it is dynamic. If events unfold in a cause and effect sequence, the process is deterministic. And if its behavior is unpredictable and non-linear, it belongs to the most fascinating aspects of life: nature, relationships, economies, and human creativity. For a long time, science assumed that with enough information, everything could be predicted. Chaos theory challenges this, showing that even in a world governed by rules, absolute certainty is unattainable. Even simple systems like a swinging pendulum or a house of cards can suddenly collapse into disorder. As systems interact and small changes build up, their outcomes become wildly unpredictable. Rather than dismissing science, chaos theory acknowledges its limits and reminds us that uncertainty is a fundamental part of reality. Chaos versus randomness. Chaos and randomness may seem similar, but they are fundamentally different. A chaotic system never repeats itself exactly, even though it remains identifiable, while a random system can fall into repetitive cycles because it has no constraints preventing it from returning to a previous state. Each chaotic system operates within its own phase space, meaning its movement follows a unique trajectory that never repeats precisely. If we were to plot the movement of a chaotic system, the resulting graph would contain an infinite number of points, with no two occupying the exact same position. Initially, these points may seem random, but over time, hidden patterns and structures emerge, revealing the underlying order within chaos. Fractals, the geometry of chaos. Fractals are unique mathematical objects that reveal a hidden order within chaotic systems. The term fractal, introduced by mathematician Benoit Mandelbrot, describes shapes that exist in a space between dimensions. A key idea behind fractals is that patterns at a small scale resemble patterns at a larger scale, a modern interpretation of the ancient concept of microcosms and macrocosms. For example, the jaggedness of a single mountaintop is similar to the rugged contours of an entire mountain range, demonstrating a consistent fractal dimension across different scales. Unlike traditional Euclidean geometry, which focuses on smooth, regular shapes, fractal geometry embraces irregularity and complexity. This approach allows scientists to quantify seemingly unruly natural structures, such as coastlines, tree branches, and even turbulent fluid flow. Fractals are formed through recursive processes, simple rules that repeat endlessly, generating intricate and self-similar patterns. These structures, often visualized as mesmerizing images, serve as representations of dynamic systems, illustrating the balance between chaos and order. the butterfly effect, and phase transitions. The butterfly effect highlights how small changes in a dynamic system can lead to sudden, transformative shifts. One of the most common examples used by complexity theorists is the sand pile. While adding a single grain of sand may seem insignificant, at some point, one final grain will trigger a cascading landslide. This phenomenon is known as a phase transition, where a system shifts dramatically from one state to another. Chaos theorists have observed that these transitions, though seemingly unpredictable, follow certain stable patterns. The systems most susceptible to these shifts are those that exist on the edge of chaos, where order and disorder interact in a delicate balance, making them highly sensitive to even the smallest changes. Chaos, determinism, and the limits of predictability. In 1814, mathematician Pierre-Simon Laplace proposed that if we could gather complete information about the universe at a given moment, we could use physics to predict everything about the future with absolute certainty. However, as our understanding of complex systems has evolved, we've realized that predictability is far more limited than Laplace imagined, even within Newtonian physics. The need for probabilities in forecasting isn't just due to gaps in our knowledge or the randomness of quantum mechanics. Instead, it often stems from chaos, a classical phenomenon where even tiny differences in initial conditions can lead to drastically different outcomes. This means that even though Newton's laws of motion are deterministic, they don't always produce a perfectly predictable universe. Newtonian physics versus chaos. While quantum physics deals with uncertainty at the smallest scales, Newtonian physics provides a reliable way to predict the motion of everyday objects. Unlike quantum mechanics, Newtonian physics is deterministic. If you know an object's position and momentum, you should theoretically be able to predict its future motion with precision. Newton's equation, force equals mass into acceleration, allows us to calculate an object's movement step by step. As long as quantum effects are insignificant, Newtonian physics works flawlessly. However, even with precise equations, predicting a system's long-term behavior has limits. Small uncertainties in the initial conditions can lead to vastly different outcomes over time, a key idea in chaos theory. The core lesson of chaos theory is this: even if a system is governed by clear mathematical rules, tiny uncertainties in the present can make the future unpredictable. The present determines the future. But an approximate present does not necessarily lead to an approximate future. That's all for the video. Thanks for watching, and don't forget to subscribe for more videos.